Okay, this is Tuesday, April 3rd, and it's section 28.3, polar functions and curves. So we're going to express x and y in terms of r and theta. And we're going to sketch polar curves on the polar grid, and we're going to use polar functions to represent real-world situations. Okay, so number one, reason abstractly. Given a point described by a rectangular pair x, y, use the diagram and trigonometry to express the polar coordinates of r and theta in terms of x and y. So how do you think you're going to do this? So you label this x. Just a second. Hello? I'm at school. Why don't you come out here and then we can drive to the flood and then you can drive me back here. All right. Let me know when you're out there. Bye. Okay, so we have this little picture right here. See this picture? See how I drew a right triangle there? X, Y. How do you find R? Well, since R is just the hypotenuse, you would find R by taking the square root of x squared plus y squared. That's how you find the R in polar coordinates. How do you find the angle? This angle is the arctangent of y over x. And that's how you do it. Same stuff we've been doing all along. So in example A, it said you have an approaching aircraft, which is 9 miles west and 9 radical 3 miles north in the air. So they give you these coordinates. Since it's west, notice they give you a -9. And then they want you to find the r coordinate. So they did the square root of all of these. And they got this. And they got this, which is 18. That's the r coordinate. So you would write 18, comma. Then to figure out the angle, they do arctan of the y over the x. Now you got to keep in mind that if it's negative positive, you're in the second quadrant. That's very important to your angle. So your angle has to be between, it's telling you right here, between 90 and 180. So when you divide these 9s out, you end up with this negative radical 3. And you should know that that's 60 degrees, but in the second quadrant, that's 120 degrees. So that's how I wrote the answer is 18 and 120. And that's what we're doing here. So try these A. So to figure R out, you're going to do the square root of 12 squared and 9 squared, which is 144 and 81, which is 225, which is 15. That's your arc. And then you have arctangent of 9 over 12, and they're both negative, so what quadrant are we in? If they're both negative, we should be in the third quadrant. So your answer, that means that your angle has to be something between 180 and 270. Make sure your answer is somewhere between there. So when you do this, 9/12 on your calculator, it's arctan. What did I say it was? 9/12. So you get 36.87, 36.87, but that's just the reference angle. So you're going to take 180 plus that. So 180 plus this is about, what, 216.87. So the answer to try these A is 15, comma, about 216 degrees and 87 degrees. Sounds good. So why don't you guys try C? I don't have any room for B, so let's try C. First of all, what quadrant are we in? What's negative 12, 5 quadrant? Negative 12 is left and up, so you're in the second quadrant. So your angle has to be between 90 and 180. Make sure it's in between there. So first we have 12 squared and 5 squared for your R, which is 144 and 25, which is 169, which is 13. So far, 13 is part of your answer. For the angle, it's arctangent of 5/12. 22.62. So you get 22.62, but that's not your answer. That's the reference angle. So we're going to take 180 minus this. You always subtract with an x-axis number. 180 minus 22.62 for a 157 0.308 degree angle. That's how you do it. In 2, it says use appropriate tools strategically. They're basically saying that when you punch this in your calculator, 9 radical 3 divided by 9 arctangent, if you actually use, you know how I always say do not use negatives because they mess you up? We have 9 radical 3 divided by negative 9. It gives you negative 60. It gives you a 4th quadrant answer. And they want to know why it gives you the angle that's located in the 4th quadrant. That's because back when we did reference angles and principal values, they give you the answer closest to 0. So it gives you negative 60 because that's called a principal value for arctangent. So if you guys remember anything about that, that's why I never have you type in negatives. You should just work with the reference angle, not the principal value. This is principal value. You should work with reference angle. So that's why I never use the negative. So you work with 60 degrees, and it's easier to add and subtract with 60. So anyway, there's a way that you can do all this stuff on your calculator. So to convert between rectangular and polar coordinates on a graphing calculator, you're going to start by pressing second angle to access the menu. So let's do that right now. Second, it's really second apps. You see that apps right above apps is angle. And we already practiced a couple of these. We were doing polar to rectangular, 7 and 8 in the last section. Now we're going to do 5 and 6. We're going to get rectangular form into the polar. Actually, I would like to do the problem that we just did. Let's go back up to try these A. Okay? So if I press number 5, it tells me to give you, you just have to enter the order pair. So it's like negative 12, comma, negative 9. Oh, yeah. You have to get both. And you press enter, and it gives you the 15. Remember the 15 we got? Isn't that awesome? And then press second angle again. And this time press 6. Now we want the angle. So you would press negative 12, comma, negative 9. And it gives you that. Where's it at? Oh, that's not the answer I got. Oh, you know why? They're giving us the 3rd quadrant angle. They're doing the negative one. I gave the positive one. If you do negative 143, that's the same thing as 216.87. Ooh, I don't like that. I like the positive angle. Ew. Don't like that. Do you guys like that? I don't like that. So let's do the ones they said. Use a graphing calculator to convert each order pair from rectangular to quarter, and then round each coordinate to the nearest tenth if needed. All right, so negative 3, 3. We're doing negative 3, 3. We're doing 3A. So we're going to press second apps, 5. Then you're going to press negative 3, comma. Comma's above 7, by the way, if you can't find comma. 3. And the R is 4.24. So you just go like this, 4.24. And then the angle would be arc. Oh, I'm sorry. I started doing arctan. Sorry, guys. We're supposed to be doing this key here. We're doing 6. So that you would do negative 3, comma, 3. And it gives you 135. This time they did give you a positive angle. Looks like they're going to give you the smaller angle. Like in this last one, when I showed that last one, 216 is a bigger number than negative 143, so they gave you the smaller one. 135, the negative of that is going to be like in the 200s, so they're giving you the positive one this time. Let's just do the one more. Let's do this 5.8, 1.6. Second apps, 5, 5.8, comma, 1.6 for 6.01. We'll go 6.02. And then second apps, 6. And then we're going to go 5.8, comma, 1.6 for 15.42 degrees. Pretty easy. So it says here, pilots have a radar screen in the cockpit of the airplane. When landing in overcast weather conditions, the radar screen becomes their eyes, guiding them to the runway for landing their aircraft. This radar screen is also a polar grid. with the pole on the screen giving the location of the instrument landing system, the transmitting tower, and the polar axis denoting due east from the instrument landing system. The bright point on the screen shows the location of the aircraft relative to this ILS transmitting system. So usually this transmitting system is positioned at the end of a runway. This positioning shows the pilot exactly where the beginning and end of the runways are located. So from the ILS transmission, the pilot uses the cockpit radar screen to maneuver the airplane towards the pole, which locates the beginning of the runway. So they like to have the pole at the beginning of the runway. Polar curves of this form, r equals f of theta, can be used to describe landing approaches for aircraft pilots. So the maneuvers performed by pilots are called landing approaches. They have strict landing approach procedures that must be followed to keep an air traffic orderly and safe. These landing approach procedures are similar to traffic lanes usage for cars. So with all that said, let's try 4. The ILS signal indicates that the landing approaches towards the south. The scope of the airplane uses concentric circles with radii in terms of 1 mile from ILS runway signals. Use the polar grid below to sketch the landing approach that is described by the polar function r equals cosine theta for 0 to 90 degrees. Begin by plotting the location of the plane when theta is 0, 30, 60, and 90. So guess what? We're going to learn something new here. Well, let's do it by hand first. So we have 6 cosine theta. And our thetas are going to be over here. So they want us to do 0, 30, 60, and 90. Okay? So if you punch in cosine of 0 is really 1. You can't see what I'm doing. So I'm making a little t-table here. So 6 times, so this is really 1. So this is 6. So 0 degrees, 6. The coordinates for that would really be 6, 0 degrees. So 0 degrees is here. So 1, 2, 3, 4, 5, 6. It's right there. Wish I could get all this on here at once. The next one, 6 cosine of 30. Well, 6 cosine of 30, we'll just punch that in our calculator because I think that is a decimal. 6 cosine of 30 is 5.2. So that's really 5.2 and 30 degrees as polar coordinates. So 30 degrees is here. 1, 2, 3, 4, 5.2. Oops, it's a little bit more. So, shoot. These are really bad for my eyes. 1, 2, 3, 4, 5. I think we're a little bit more. It's actually bigger. It's right there. 60 degrees. 6 times cosine of 60. Well, cosine of 60 is 1/2. 6 times 1/2 is 3. So it'd be 360. So 60. So it's 1, 2, 3. And then 90. Cosine of 90 is 0. So 6 times 0 is 0. 90 degrees and 0 is right here. So it kind of looks like this. So it says, describe the type of landing approach that is sketched in part A. The landing approach appears to be semicircular. What do you guys think? Think that's a good word? Your graph represents the landing approach for aircraft. However, the graph of this landing approach is only part of the complete graph of the polar curve. Using the polar grid shown below, give a complete graph of r equals cosine theta. Indicate the interval values for theta that gives this complete graph. So basically, you would want to keep going, like maybe do 120 degrees, 150 degrees, 180 degrees. Okay, so what's 6 cosine of 120? So the cosine of 120 is negative 1/2, but you guys can do all these on your calculator. 6 cosine of 120, it's going to be negative 3. So 120 is here. Okay, now be careful. 120 here, but it's negative 3, so it's going to go this way. I'm almost going to, well, I'll do it here. 1, 2, 3. I'm going to graph what we had before. We had 6 and 0, right? And we had 5.2 and 30. We had 3 and 60. And then we had, so this is where we're at right now. So if you did 150, 6 cosine of 150, you get negative 5.2. So at 150, you're here, but you're at negative 5.2. So you're going to go 1, 2, 3, 4, 5.2. Remember the negatives go on the opposite side of the pole. And 180, what's the cosine of 180? Cosine of 180 is negative 1, so that's negative 6 and 180. So 180 is here, but you have to go negative 6, so you're actually where you started. So this is the complete graph of r equals 6 cosine theta. Let's do this on our, now you guys ready for this fun thing right here? I'm going to show you a different mode. Go to mode. Go down where it says function. See where it says function right there? See how it's blinking? Go right to polar and press enter. And then press y equals. Look at that. We got just r's instead of y equals. Isn't this fun? And now we're going to press in 6 cosine of theta. And press graph. Oh, you'll notice that it's going really slow. It's going so slow, so we have to do something. We have to go to window. We're going to adjust this. So 0, a theta min and max. Let's go 0 to, we're in degrees. See, they're in radians on my calculator. So we're in degrees. So let's go 0 to 360, first of all. Now this theta step will be fast or slow. We might adjust this. The x min, I think we're fine. And the y min, I think we're fine. Let's see. Just by changing it to degrees, let's see what happens. All right, it's still going really slow. Look, see how slow it is? So what we have to do is press on right now to stop the graph. Go back up to window. Let's increase this to by like 1. Just go, a whole number, 1. Theta step 1. And now it goes a little faster. And there you go. So watch what happens. Press window. Actually, press on. Stop it. Press window. Watch what happens if I made this like 20. If you go too fast, it makes now it's not like smooth anymore. Press on, go to window. Watch what happens if you press it to like 60. It's so crazy. It's like when your brain's going too fast. That's why you should never do any kind of drinking or anything like that, because that's what it does to your brain. It makes it think different things that aren't really there. So you don't want to affect the speed of things. You want to go to normal speed. So we're going back to theta step. We're going to go to 1. And then you graph, you get the polar curve. Now, remember this t-table that we did right here in the book? Could we just get those same numbers by looking at a t-table? We sure can. Just press second window. Press on. Second window. We can start our degrees at 0, and we went by 30 degrees. And now we can go to second graph. And all those numbers, there's 0, 6, there's 35.2, 63, all that stuff. Hello? Are you out front? All right, give me 1 minute to finish this video. Bye. All right, so wasn't that fun? That's called a polar curve. Now, all these polar curves have names, and we're going to be doing these in this next section over here in 29.1, but that's not till I come back from break. In 29.1, we're going to do all these polar graphs and stuff that look these crazy shapes. That's when I come back. So this was just the introductory to what we'll be doing when we come back. So really quick, example B on page 389. So anytime you have a polar curve, such as r equals 6 cosine theta. Oops, you can't see this. R equals 6, that's called a polar curve. Anytime you have a polar curve like this, you can transform things, okay? So we have this r equals 6 cosine theta by writing it as an equation using the rectangular variables x and y. So we're going to be using what we've learned all along, that anytime you need r, you need x squared plus y squared. And that, well, cosine of theta is always x over r. I don't usually use that. Ooh, this is not very pretty. Oh, this problem's hard. Let me look at this for a second. Cosine is saying adjacent over hypotenuse. And then the hypotenuse r is radical x squared plus y squared. Does that make sense to you? Since cosine is adjacent over hypotenuse, and we know that the hypotenuse r is x squared plus y squared, they're writing the cosine like this. It says it substitutes expressions r and cosine of theta into the equation of the polar curve and simplify this. So since we know that r equals this, you put that there. And since we know cosine equals all of this, you put that there. And what they did basically is they cross multiplied. So they're kind of leaving out a step right here. So over here they had, let's do this. They have x squared plus y squared. I'm going to multiply the 6 with the top. If you cross multiply these, the radicals are going to cancel, and that's how they got the x squared plus y squared equals 6x. Now from here, they're going to complete the square. So they're going to bring the 6x to this side, leave a space for a new term, and they're going to put a y squared here, set this equal to 0. So what's half of negative 6? You should say negative 3. Negative 3 squared is 9, so you'd add a 9 to the other side. And if you complete the square, you get x minus 3 squared plus y squared equals 9. And this is the equation of a circle that has center 3, 0 with radius 3. Now, if we did this on that last problem, if we went over to this polar graph and we had a center of 3, 0, there it is, with a radius of 3, wouldn't we have this circle? You guys see that? So that polar curve is just a circle. So when you see the equation r equals cosine theta, it's equivalent to this in its rectangular form. Does this transformation example B confirm your answers to item 4b? Semicircular? We said no. 4b was actually supposed to be circular, so it's not confirming it. So no. Sketch the complete graph of 4 sine theta. So when you see a 6, half of that is 3. The center is going to be half of that. The center is going to be half of that at 3. Cosine means you're on the x-axis. That means you're symmetric to the x-axis. Sine means you're symmetric to the y-axis. Little things you're going to find out here when we do these. So when it says complete the graph of 4 sine theta, here's what I know. That we're going to be symmetric to the y-axis here. It's not going to be horizontal this time. It's going to be up here. Because if 4 is positive, we're going to be high. If it was negative, we'd be down here. And the center is going to be half of that at 2. So my guess is that the center is at 0, 2, and the radius is going to be 2. Transform the equation of the polar curve, but we're going to do it right here. Ready? 4 sine theta graph. See how the diameter is 4. So the 4 is basically telling you the diameter. This 4 is the diameter of the circle. The sine is telling you that it's symmetric to the y-axis. So if you were just going to do a quick little picture here, 1, 2, 3, 4, the center is 2, but you do need some help along the way with these points. So we're going to go to the t-table. I've already got the 30 set up, remember? So we're going to have a point at 0, 0, which is right here. That's at the pole. 32. We have 63.5. There's your 94, which we already have that one. 123.5. We have 152. And then we go back. So there is your picture. And that's it.